Welcome to this explainer. Today, we are going to demystify the massive invisible infrastructure that completely powers our digital lives. I mean, today's internet is arguably the largest engineered system ever created by mankind. It is this intricate, global machine made up of hundreds of millions of connected computers, communication links, and switches. But how does it all actually work? Is there any real, reliable structure to all this apparent chaos? The answer is a resounding yes. And figuring out the actual architecture of the internet isn't just possible, it's absolutely fascinating.
Let's kick things off with a massive number, 25 billion. The source material notes a jump from about 5 billion connected devices back in 2015 to a projected 25 billion by 2020. That is an explosive, almost unbelievable rate of growth. And we're no longer just talking about plugging in traditional desktop PCs or standard Linux workstations. The very definition of what makes up the network's edge is evolving right before our eyes, shifting the entire landscape of global connectivity in some really profound ways.
And here's the wild part. These billions of devices aren't just laptops and phones. They're everyday objects that now make up the edge of an engineering system used by over 40% of the world's population. It's a huge, diverse ecosystem of non-traditional stuff talking to each other constantly. I'm talking about the thermostat adjusting your living room temperature, or the traffic control systems guiding your morning commute. Honestly, the term computer network is almost starting to sound a bit dated when you consider all these unconventional things hooking up to the global grid.
Now, to get a solid grasp on how this global system actually works without getting totally lost in the weeds, we're going to follow a pretty straightforward path today. We'll look at the networked world, dive into a top-down approach, explore why principles matter more than protocols, ask what actually is the internet, and finally wrap things up with a super helpful highway analogy.
All right, Section 1, the networked world. Let's meet the folks who actually mapped all this out for us.
Everything we're covering in this explainer comes straight from the 7th edition of the absolute gold standard in the field, computer networking, a top-down approach. This text is phenomenal. It's been translated into 14 languages and used by over 100,000 students and practitioners all over the world. It really lays down a perfect foundation for understanding not just the networks we use today, but the networks we'll be using tomorrow. And the minds behind it are Jim Caroz from UMass Amherst and Keith Ross from NYU and NYU Shanghai. These guys aren't just top-tier researchers doing their own thing in a lab, they're incredibly dedicated educators who have fundamentally shaped how computer networking is taught around the globe.
Between the two of them, they bring over 60 years of teaching experience. 60 years! That means they've spent decades in the classroom figuring out exactly where people like us get stuck, and they've used that invaluable insight to design a learning structure that just cuts right through all the complex jargon.
Which brings us to Section 2, a top-down approach. They basically flip the script on how we learn this stuff.
So, what does top-down actually mean? Well, instead of boring you to tears by starting at the bottom with physical copper wires and raw electrical signals, which is how it's traditionally taught, they start at the very top. They start with the software and applications you already know and use, and then slowly peel back the underlying layers. By flipping the script like this, you get a much clearer understanding of the why before you ever have to dig into the how.
It's honestly a brilliant motivational tool. As they mention in the text, it immediately grounds all this abstract engineering into your actual everyday reality. Instead of starting with a confusing wiring diagram, you start with web browsing, you start with email, and once you see how an application actually functions at that top level, you naturally get curious about the invisible network services that are working behind the scenes to support it.
Moving right along to Section 3, Principles over Protocols. This is how you build knowledge with a seriously long shelf life.
Here's the deal. Rather than having you memorize specific, fleeting code that's just going to change in a few years anyway, they prioritize teaching fundamental networking principles. We're talking about massive core problems like congestion control or cryptographic security. These have a huge shelf life. Think about it. The specific code for a routing protocol might look totally different next year, but the fundamental mathematical challenge of finding the fastest route between 2 points on the globe, that stays exactly the same. By focusing on these principles, you get a foundation that outlasts any single tech trend.
Okay, Section 4. What is the internet? It is time to tackle the big foundational question.
The source breaks this down into two distinct views. On one side, you've got the services view. This looks at the internet as a platform. It's the invisible stage that allows your streaming video, your messaging apps, your emails to do their thing. But to really grasp the architecture, you also need the nuts and bolts view. We have to zoom in and look at the actual microscopic, physical hardware components that are transporting all those bits and bytes. And when you zoom in on those physical nuts and bolts, it's wild. You see this massive web of end systems, or hosts, connected by communication links and navigated by packet switches, like routers. The sheer diversity here is crazy. You've got home networks, mobile networks, global ISPs, all just patching into one another. Basically, when a device wants to send data, it chunks that data up into little packages called packets and fires them across these links, whether that's copper wire, fiber optics, or radio waves, until a switch catches them and forwards them closer to their destination.
Let's jump into Section 5, the highway analogy. We are going to translate all of these abstract concepts into something super intuitive.
To really visualize this, think of the network like a giant physical logistics system. Your data, those are the cargo trucks, the packets. The communication links are the highways and the roads they drive on. The routers are the intersections guiding the traffic, and the end systems are the final destination buildings. It's the exact same logistical puzzle as physical shipping, just happening at the speed of light. Every single time you load a web page, you are literally dispatching a fleet of digital trucks across complex global intersections, so they can arrive at your device and unpack their cargo right onto your screen.
So, bringing it all back around, I want to leave you with this provocative thought. With 25 billion devices out there sending these digital trucks down the highway, how on earth do we prevent a global traffic jam? Just think about that for a second. Millions of uncoordinated devices acting as factories, dispatching billions of packets every single second with absolutely no central brain directing the traffic. The fact that the whole system doesn't just immediately collapse is an absolute marvel of engineering. Figuring out the elegant, almost magical rules that prevent that global gridlock is what makes computer networking so incredibly rewarding. Thank you so much for joining me on this explainer, and keep that curiosity fired up.